I think I can start. So today we're going to talk about a slightly different topic, which is interpolation. Let me see if I can share my iPad. Where is the chat? Okay, so and so kind of like the idea here, um, you can think about it like experimentally, where like maybe you have like a list of measurements. So you know, maybe you're collecting data. uh, uh, Relating to different quantities. Okay, relating to quantities X and Y. I mean, so like it could be quantities which you could think like maybe they are like correlated in some way, statistically speaking. So it could be, you know, I mean, like if you were talking about like social sciences, it could be more like maybe income versus like, I don't know, what could it be? Like could or maybe it could be height and weight. Maybe you expect that there's some relation between those two variables. That's reasonable to some extent. Or like, it could be temperature and pressure, or like, position, like time and position, like, it can be just whatever two quantities, that like maybe you expect to be some sort of like relation between them. And then like if you make a certain number of measurements, right? If you make a certain number of measurements, if you make a finite number of them, then you would just get like kind of like a bunch of points like scattered on the plane, right? So you could get something like this, right? And like, oh, okay, so here, how many am I drawing? I'm drawing, I guess, 6 points, right? So like, like this could correspond to the value, like the values for the first measurement, the second measurement, third measurement, fourth one. Oops, fifth one and sixth one. Of course, in practice, like in anything realistic, like you could be talking about thousands of points or like hundreds of thousands. But like just to keep it like things simple, like as a motivation, like you could just imagine like having collected a few like data points. Okay, and so the idea of like interpolation is to try to kind of like maybe find a curve that fits those data points. So kind of like the idea behind interpolation is to find a curve. Okay, so I'll take advantage of the fact that I can just copy paste the points that I just drew. So like if you copy paste this picture, um, maybe the curve could look something like this. Okay. I mean, like that could be like that. That is something that you would call like the interpolating curve, right? So far so good. Is that make kind of making sense? So for now, I mean, kind of what I'll start telling you today about is like what sort of curves you would like to work with. Um, like what are some natural conditions that you could try to trying to solve this type of problem. Right? It is similar to like a sort of like linear regression. Um, but I guess like in linear regression, kind of like the word says it, like you may just like want something that's like a linear function, right? But it is kind of like a similar concept. Um, for kind of like for like the first half of the week, which I guess is just today and tomorrow, we will do kind of like interpolation in the sense that it is perfect, meaning that the curve does pass exactly through all the points. And then Wednesday, Thursday, I'll do more kind of like the kind of like how now I'm losing the name, like like this when there's like an error that you are allowed to like accept, so like you don't necessarily need the curve to pass precisely through all those points, but you want to minimize kind of like the error between the fitting curve that you're going to use and the points that you measure. So like it's kind of like but for today and tomorrow, I guess when we talk about splines, it will be kind of like you have those points. You don't care necessarily whether there was like any measurement in the error when you collected the data. So you would like a curve that passes literally through all of those points without like any uncertainty, And then like on Wednesday, Thursday, we'll talk about more like what if there's some uncertainty, or maybe there are good reasons for why you wouldn't want the curve to go through all of them precisely. Um, but yeah, it is related to like linear regression, correct? Yes. Um, it's kind of like in the same spirit. But so for just like as a remark, well, actually two remarks, so like that I'll make. Again, for now, we are interested in curves that pass exactly through all the points, so we do want the curve to pass through all the points. So like there are kind of like no error consideration. That's what I'm trying to say. So we're kind of like ignoring like some sort of like uncertainty. Oh, least squares. Like, sorry, that was like the phrase I was trying to like had it like on the top of my head, like top of my tongue. Like then we'll talk on Wednesday, Thursday, kind of like more of like a least squares method, where like you kind of like are minimizing like some sort of like error. Um, but for now, kind of like the curve passes precisely through all of them. Um, and then the other thing that the other assumption that we'll make, which is like a reasonable one, is that no two points that we're trying to pass through have the same x values. So what I mean by that is like, going back you know, to what I was saying a bit earlier, like we are trying to ignore like a situation like something like this, where maybe there's like an extra point that is literally, you know, like kind of like above one of the other points, because the reason for that is that we do want to kind of like try to interpolate with the function, right? And if you're trying to interpolate with a function, like if you remember, like a function cannot be completely vertical, right? Like you cannot have like a function, like for a function, like a single value of x can only be related to a single value of y. So something like there would not, if of course there is a curve that passes through all these points, right? You can still draw like a curve that goes through all of them, but then like it wouldn't be the graph of a function. And so we do want to work with functions for now, and for most of the course, I would say. So like something like this, like would not be something that we try to tackle directly. So because let me write that down, because we do want the curve to be like the graph of a function, because we want the curve to be the graph of a function. Is that making sense? So it's kind of like more like for, our purposes of like having like simplify our lives a little bit. Okay. So like, the first time you think about this, like if you're trying to find now instead of like using the word curve, I will use the word function. If you're trying to find a function, that passes through all these points, you know, kind of like at a practical level, the easiest thing you could try to work with is with polynomials, just because polynomials are well understood. And there are many theoretical reasons for why polynomials are useful, like functions to work with. So, kind of like today, what we'll focus mostly on is trying to find a polynomial that passes through all of these points, and this is called like the Lagrange interpolation. Okay, so I'll kind of like show you how that's supposed to go. Um, and I'll also like remind you a little bit about polynomials, just that we are all like on the same page of what do you need to remember from them. So so today we will do the Lagrange interpolation. And this is the same Lagrange from Lagrange multipliers, from Lagrange mechanics, from Lagrange everything. I don't think there's like another one that had the same last name. There are other cases where like mathematicians have like same last name, but I think in the case of Lagrange, it's only one Lagrange that's kind of like the one that's famous. Um, so it's like not too hard to miss in this case. So Lagrange interpolation, which is trying to find a polynomial that passes through all these points. Okay, find a polynomial passing through these points, through the given points. Okay. So again, let me kind of like give you some quick reminders about polynomials. So some facts about polynomials. And just to get some like notation, like also more like uniform. Um, so for example, like the polynomials, like the main way to distinguish them is by their degree. Okay, so the degree of a polynomial is kind of like one of the most important facts. So degree one polynomials. Let's just like write down some concretely. You know, degree one. They're literally just like the linear functions that you know of, right? Which is like typically how you know this is how you would usually refer to them, like the linear functions, like like a traditional way of writing like a line is y equals mx plus b. We do want a more like standardized notation because we do want to talk about different degrees of polynomials. So a better way now for me to refer to them will be kind of like in this way. Instead of writing y equals mx plus b, I'll write p1 equals C0 plus C1x. Okay, it's like change of notation, but okay, what is a one here? Like when I say P is for polynomial, so that's hopefully, reasonable. The one tells me the degree is going to be referring to the degree, and then this is just going to, I'm just relabeling the constants, but like that way, kind of like we'll keep better track of like the like the terms. Okay, so for example, just to kind of like make it more clear, like why this is like a better notation. Like if you have like a degree two polynomial would be a parabola, right? And again, like you can draw like a parabola if you want. This is maybe how it looks like. Like the traditional way in which you may have been given a parabola was something like y equals ax squared plus bx plus c, which is all fine. But again, it's not super convenient from this perspective when you want to talk about all the polynomials of different degrees. So again, like just switching to this like more standardized notation, you would write P2 of x, right? Because now it's a degree 2 polynomial, would be C0 plus C1x plus C2x squared. Okay? Uh, so you see, like the index, which is like how you would refer to these numbers, kind of like keeps track, is like paired with the degree of the exponent, like with the exponent of x. So that kind of like looks nicer. And like a cubic, like a cubic would be then like, for example, like a cubic, which is a degree 3 polynomial, would be P3 of x equals Z0 plus C1x plus C2 x squared plus C3x cubed. Is that making sense? That and like as you can imagine, like the degree n, just to kind of like write it down, degree n would be Pn of x. If you remember from Calc 2, the sum notation, like I guess it would go from I equals 0 to n of ci x to the I, right? And that kind of like, if you were to write it down term by term, it matches exactly with what I have been writing. So kind of like the idea is that the constants are like the ci's, right? And they are kind of what specify the polynomial, right? So I guess I will refer to them sometimes as parameters or constants, but the ci's are the parameters. Or coefficients, like maybe it's like a better way of referring to them, which specify the polynomial. Is that okay so far, so good? Any questions up to this point? And then, the kind of like the fundamental fact about polynomials is like what's sometimes called like the roots or the zeros of a polynomial, right? And this is kind of like the fact that we will use most of the time for this type of interpolation problems, right? Is that if you have a polynomial, right, of degree n, then the equation p of n equals 0, right? Like, again, just for examples, you could think of x squared plus 1 equals 0, or x cubed plus x minus 1 equals 0. Like, take your favorite polynomial, set it equal to 0, whatever polynomial in the world. Um, what is important, or like, 2x cubed, just to have something that doesn't start with 1. Uh, the fundamental fact about polynomials of a certain degree is that, if this is degree 2, then the most that can happen is that you have two solutions or two roots. That's how you would call this. Or if this is because it is degree 3, the most that would happen is that you can have at most three solutions to this equation, right? So can have n solutions to this equation, or like n roots. Like, because sometimes like you call them roots. Um, like then like there's like a more fancy result which is like the fundamental theorem of algebra that says that if you allow complex numbers, then they're exactly n roots, if you are okay with including repetitions. But that we won't require. But the fundamental theorem of algebra says a little bit more than that, that there are exactly n solutions, uh, if you accept repetitions and complex numbers, right? But I'll just mention it because it's like a fun fact, but we won't really use it. So, like as a remark, the fundamental theorem of algebra says that Pn equals 0 has like n solutions if you allow for repetitions and complex numbers. If you allow for repetitions. Is that okay so far, so good? Is that making sense? Any questions up to this point? Okay, and then the other important thing about polynomials is kind of like, like how many points in general do you like are you required to give to specify a polynomial of a certain degree? So for example, let me say like a little bit about that. Okay, so like let's just go back to degree 1 for a moment, because we kind of like know that one pretty well. Um, Again, like I'll just write it in this like notation, like this is like a line, right? So like, kind of like the usual thing to say is that to specify a line, right? To specify a line, or if you give me 2 points on the plane, right? Maybe this is like a better way to say it. If you give me 2 points on the plane, I can find a line that passes through these 2 points, right? Well, at least like again, like when the points don't share the same x value, which is kind of like an assumption that I'll be making throughout the entire class, because again, we want like functions. But kind of like the idea is that 2 points, right? 2 points on the plane specify a line or a degree one polynomial. That's how I would say it. And like there's like there's kind of like I will kind of like again, it's like a very well-known fact probably, but I'll kind of like present it in a more like linear algebra way, right? So because it's kind of like will be useful for what I'll say in a bit later. So like if you thought about like these 2 points as being given, so there are points that you know, right? Like determining the polynomial is the same as saying that you have to find C0 and C1, right? So the goal would be to find C0, C1 in terms of x0, y0, x1, y1, right? Sure. And if you think about it, then how could you do that? Well, if you want the points, if you want the polynomial to pass through those points, right? What that means is that if what that means is that that should tell you that P1 of x0, right, should be y0, and P1 of x1, right, should be y1. Right, because that's kind of like what it means to say that the polynomial at x value x0 has y value zero, y0, and that at x value x1 has y value y1. Is that making sense? But then again, what does that mean concretely? If you use like the formula for the polynomial, right? It would be that C0 plus C1 x0 has to be equal to y0, and that C0 plus C1 x1 has to be equal to y1, right? Is everyone with me so far so good? And this is kind of like a bit confusing because like here what I'm trying to find are the values for z0 and c1, right? So kind of like my unknowns are z0, c1. The ones in red are known, right? That is actual numbers, right? That's numbers that you know. Kind of my variables here are c0 and c1. So one way to think about it in terms of like linear algebra here, right? Because z0 and c1 are the unknowns, is that you make a vector, right, whose entries are C0 and C1, and that is the same as you get this system of equations. So I'll put one like in red also. Is that making sense? So like if you're trying to find C0, C1, that is the same as trying to solve this system of equations, right? But what is a determ? I don't know if you remember. Like this is like a square matrix, right? A square matrix has a unique solution when the determinant is not zero, right? So what is the determinant here? It's like x1 minus x0, which is not zero because I told you we're assuming that the points don't share the same x value, so this is not zero. So the inverse. So we can. I think I don't know if you miss a word in the at the beginning of your question. So we can you can solve a system of equations to find the weights if that's what you meant your question as. Yes. Uh, yes, yes, yes. So you can right. Like I'll do it for like one more time for the quadratic one, just to kind of like show you that it kind of like takes the same like shape. But yeah, kind of like what I'm saying is that trying to determine the coefficients or the I mean I will use the word coefficients instead of weights, but it's kind of like the same idea, right? Trying to determine the coefficients of the polynomial can be reworded as a linear system of equations. Yes, yes, yes. Um, But kind of like the idea, what I want to show from this example is that, um, it's useful to have like this perspective of linear algebra because the way to think about it, just to go back for a second, is that there are two unknowns, right? There are two things that I don't know, C0 and C1. So if I don't know two things, if I'm trying to find a solution that's unique, I should aim for giving two data points because with two data points, then I can write two systems of equations, right? So that's kind of like the mentality to have here. And so, for example, in the case of a parabola, let me do the parabola as well. If you think about the parabola, if you think about it now from the parabola perspective, right? Then how many things I don't know? I don't know three parameters or three unknowns, right? I don't know C0, I don't know C1, I don't know C2, right? So again, kind of like the rule of thumb, because you don't know three things, is that you would like to set up a system that has three equations, right? Because three variables, three equations, like what you would expect is for there to be a solution, a unique solution, if everything works nicely. So in this case, again, you would like to say, how can you give that out? Okay, so I should specify 3 points, right? Like for a parabola, you should try to give, like a parabola should be related to 3 points. So if I have like maybe, oops, sorry, this should have been C0, C1. If I give 3 points, then kind of like you have this condition that at each point, like let me try to write it down in a slightly more simplified way. Uh, that at the point xi, the value of the polynomial should be yi, right? And that kind of like again translates into three sets of equations, right? Because I would be saying that c0 plus c1 x0 plus c2 x0 squared. Now that should be y0, okay? And then z0 plus c1 x1 plus c2 x1 squared. That should be y1. And last but not least, that's c0 plus c1 times x2 plus c2 x2 squared, right? That should be y2. Right. Kind of like, yes, 4 data points. If you were given 4 data points, what we would try to find is like a cubic, right? A degree three polynomial, correct? And then you see three equations, three unknowns, right? Again, you could rewrite them in as a matrix format because it kind of like shows more features better. So this is C0, C1, C2. And then this is Y0, Y1, Y2. Okay. And then what are the coefficients here? They are 1 x0 squared, 1 x1 squared, and then 1 x2 squared. Okay? Is that making sense? Like that would be the matrix in this case and all these things? So again, what happens here, you know, it's a 3 by 3 matrix, right? And then you would like to say, okay, if for some like if you could guarantee that this matrix has non-zero determinant, right? It would be invertible, and then that would give you like a formula for Z0, C1, C2, right? And in fact, I mean, this one is okay, it's like a 3 by 3. Like you do know how to compute. I think everyone has seen probably at some point how to find the determinant of a 3 by 3 matrix. It's not too bad to find it in this case, but like if you want it as an exercise, you could show like the determinant of this matrix is not zero again. Um, what I want you to, what I'm, the reason why I'm doing this is that hopefully it's giving you a little bit of a hint of what the structure of the matrix is in any degree, because like let's just for comparison, how are these matrices looking like? Let's compare the matrices that we have found so far. So the first 2 by 2 matrix was 1 x0, 1 x1, and the 3 by 3 matrix that we just had, right, was it would be 1 x0 squared, 1 x1 squared, 1 x2 squared, right? So even if you kind of like think about it, like there are some features that are kind of like these two matrices shared, right? Like for example, like maybe the most obvious thing to see is that they have like ones on the first column, right? And then on each row is related to one of the data points, and they are kind of like increasing in order. So for example, the next one, if you wanted to take the guess, right, would be what? 1 1 1 1, right? Then x0 squared, x0 cubed. That this would be for the cubics, by the way. Like this is like the one that you will use for the cubics. Then what? X1 squared, x1 cubed, x2 x2 squared, x2 cubed, and then x3 x3 squared, x3 cubed, right? Is that making sense that should like? I mean, is everyone convinced that that should be the next one? Like, I mean, of course you can always check it, like if you like are still skeptical, but it kind of like looks plausible that that would be kind of like the next matrix, and that it kind of like also shows why it's useful to have like a uniform notation because obviously it makes it easier to, identify what's going on in this case. So all these matrices that I'm writing for you right now, they're called van der Monde matrices. So these matrices are called like van der Monde matrices. Van der Monde was the name of the guy, by the way. So, well, last name, I suppose. Um, and uh, now it obviously it's looking less obvious, but one can show, if needed, that you can show that the determinant of these matrices is not zero, and they're all, like there are like they're not non-singular, which is like the name that you would give, and they all have non-zero determinant, and they are all invertible. Let me write it like this. Which means, like, the reason why I'm saying that, which means is that that if you have, n plus 1 points, you can find a polynomial of degree n that passes through these points. Okay, so and if, in fact, it would be a unique polynomial of degree n that passes through all these points. Is that making sense? Now, no, well, let me just wait for a second to see if there are any questions about this. Okay, so what I'll do in a moment is actually I'll show you a more efficient way of finding the polynomial. And this is like the Lagrange polynomial. Because this is useful to see it from this perspective. But if you remember linear algebra, finding the inverse of a matrix is a cumbersome task, especially like a matrix that has like this particular form, right? Like, like a priori, like it looks like all these entries would be even non-zero. So like, unless like one of the x values was zero. So it is not like it's not something that you want to do in practice to kind of like find the inverse of this matrix. Um, but it's kind of like used to put it from that perspective, theoretically speaking, because it gives you like kind of like a framework to understand the problem, which is a useful framework. But I'll still kind of like the magic of the Lagrange polynomial is that there is still like a way to kind of like write down very explicitly what the polynomial should be, which kind of like goes ignores completely the problem of trying to solve the system of equations. Like it's very direct. It's like very elegant actually, but it's still nice to kind of like know that this is also some of like the theory that's going behind it. Maybe before I explain to you how the Lagrange polynomial works, like I should kind of like this can be a part that's a bit confusing, but like the method is smart in the following way, and now I'll explain what I mean by smart. Okay, so here's like an example which seems very silly, but like that may alleviate some concerns. Like if you start thinking about it, like imagine if I got given you, imagine if I got given you the points to be like like imagine if the points that I had given you were 1 1, 2 2, and then 3 3, right? Okay. Um, I don't know if you see why I'm putting this example because if the way I'm presenting it, it sounds like, oh, there are 3 points, right? Because I gave you 3 points, you would say, oh, then you're trying to find a quadratic, right? So because there are 3 points, right? Since there are 3 points, the way I presented the method, you would try to find a parabola, right? Then you would try to find. Is that making sense? But I don't know if anyone notices something about this particular 3 points. Is there like an obvious thing you anyone can see about those 3 points? Right. They seem to be on the line y equals x, right? They appear to be on the line y equals x. So what I'm trying to say is that if you say cannot realize that, and then you just feed this to the method, what you will find is that the method forces the largest coefficient to like the coefficient in front of x squared to be zero, right? So if you feed this so if you feed this to the matrix, right? So if you feed this to the system of equations, it will give you right. It will give you the C2 should be zero. So when I say that it is a degree, when I'm saying that when you have n plus one points, you find a degree n polynomial. It's with the understanding that sometimes, like maybe the highest coefficient could be zero. So maybe I should say at most a degree n polynomial. So the method is smart in the sense that if it actually should have been like a line, and you try to feed it with a parabola, it will force it to be a line. That's what I'm trying to say by the method being smart, if that makes sense. So it's not going to produce something odd. It's not going to produce a parabola when it should have been producing a line. And similarly, if it should have produced a parabola, it's not going to give out a cubic. It really just gives you like the polynomial that's supposed to give you. So the method comes out, the output is a polynomial that should really be that one, that polynomial. So like it is fine for some of these coefficients to be zero, even the highest term coefficient. Okay. So a polynomial of lower degree than the one you set it up for. Okay. So that's a useful remark to keep in mind. That is not something that really has to bother you because the method will produce a correct one. Um, if that makes sense. Uh, so as I was saying, like the next thing that we will do is I'll give you this other way of finding the polynomial more directly, which is very clever. And this is a Lagrange polynomial, but it's a little bit different. So if you want, we can take like a 5-minute break, and then I'll tell you how to find the polynomial because it's really simple actually. Now that I said all this stuff, so let's maybe meet in 5 minutes. I'll still kind of like still stay in place if someone wants to ask me something, but I'll put like 11:25 just to do like a round it off. Um, but yeah, if someone wants to ask me something in the meantime, feel free to do so. Okay, okay, let me go back to the recording. I'm almost done, by the way. Like this is like you'll see, like it's very elegant how to find the the Lagrange polynomial. So okay, what I was saying is that this method, this perspective from the matrix is all nice, very nice, but it's too complicated because in practice, trying to solve like find the inverse of the matrix is a bit messy. So the Lagrange polynomial interpolation is kind of like a more direct way of constructing the polynomial itself that you're after. So I'll work it out first on an example, and then I'll kind of like write down the general formula. But if you understand the example well, you'll see like you can definitely will be able to figure out what the general formula should be. But I'll start first with an example. So it's kind of like that is going to be a more direct way of writing down the polynomial. So this is like a more direct. So again, I'll do it with concrete points so that you see first how it works, and then I'll write down the general formula. Okay. So here's an example. Let's say that the points were like I'll say 1, 3, 1, comma 3, then 3, comma 4 maybe, and then what I want 5, 6. Okay, so I'll do 5, 6. Okay, so I want a polynomial that passes through these points, right? Um, Again, because it's 3 points, we would aim for like a parabola. It could end up becoming like a line if necessary, kind of like as in the previous example, but at least you should set it up as trying to find a parabola. Okay, again, the way I'm going to do it is not by, I'm not going to do it like explicitly with this inverse thing and the matrix. I'll do something else first. Okay, so I'll kind of like use like a specific notation, which will be useful later. I'll just kind of like take the x values. I'll take the x values and put them into like a vector. Okay, so I'll define a vector of x values. So in this case, my vector would be 1, 3, 4. Sorry, 1, 3, 5. Sorry. Okay, so it's just like a vector that records like the distinct x values of the points, and you can like organize it so that it's increasing if you want. Like that's less important, but like that would be useful as well. So first, I'll kind of like construct like an auxiliary polynomial. So I'll kind of like write it into steps. Step one, construct. This is not the polynomial that I want. It's auxiliary. That's just meant to help you. Okay. Okay, so I'll call this L for Lagrange. The polynomial, I'll use the letter L for Lagrange. I'll just do L of x. So it's going to be x minus 1 times x minus, oh, let me use like the colors actually. X minus 3 times x minus 5. So basically, the way I'm doing it is that it is a product of three terms, because there are 3 points that you were given, and you just subtract the on a particular term. You just subtract the x value, one of the x values from x. Okay, so the x values were like 1, 3, and 5. So you do x minus 1, x minus 3, x minus 5. So kind of like the idea of like setting it up this way is that this polynomial is precisely zero. The roots of this polynomial. Oh, the L is just like for the name of the polynomial for Lagrange, and the X vector is just to say that it is going to be constructed depending on the entries of this vector, you see. It's kind of like a way to refer to the. I just want to say, because if I had given you different X values, the Lagrange polynomial would be, this auxiliary polynomial would be different. So it's just kind of a way to saying, oh, this polynomial that I'm about to construct will depend on these x values that I gave you. Like I'm more like it's like this would be a little bit too much, but I could have written it like this way, but it is a little bit of an overkill, you know what I mean? Because it looks a little bit too long. But it does mean the same. Like it's kind of like saying, oh, the polynomial that depends on the values 1, 3, and 5, because those were the x values of the points that I gave you. Is that making sense? So for example, like, if I got changed this point to a 9, if I got changed this x value to a 9, there would be a 9 here, and then this one would be 9. Um, but kind of like the idea, like the main property of this polynomial is that it is 0 precisely at the x values of the points you were given. So the main property is that it is 0 x values of the points you were given. Is that okay? So far, so good. Everyone with me? And if it helps, I'll write down like the formula in general. Like, so like that formula in general, like maybe it's useful to write it down at the same time. So in general, if x had been is x0, x1, x2, x3 up to xn, right? Because you were given n plus 1 points. If you're given, then this vector Lx would have been like x minus x0 times x minus x1 times x minus x2 up to x minus xn. Okay? So you're just multiplying out, um, like you're subtracting each of the x values from x and then multiplying them all out. And then kind of like the idea is that from like I'll still kind of, at least I'll do the example today, finish it off, because today we do have a quiz. So I do want to finish this example today, and I'll write down kind of like how the general case works tomorrow at the beginning of class. But kind of like the idea is that from this polynomial, again, you will kind of like construct three distinct polynomials. And each of these like smaller polynomials is obtained from the original one just by dividing by each of the corresponding terms. So let me actually see if let me try to see what's the best way to write it down in terms of like space. I mean, yeah. So basically, what's happening, like the way I'm obtaining these smaller polynomials is just by kind of like deleting one term at a time. So in the first case, I deleted the first factor and then just end up with this one. For the second case, I deleted the middle factor, right? I end up with this one, okay? And for the last one, I deleted the third factor, and so I end up with this one, okay? So it's kind of like, you just remove one of the x values from the polynomial in a sense, like in the same order in which they appear. Okay. And why do you do that? Because now, what's the thing about this is like the polynomial that I started with. The polynomial that I started with had the property that it was zero at all the kind of like the values of x, like at the distinct values of x simultaneously. What this polynomial, like the next three polynomials that I built, have the property that they're zero everywhere except at one of the x values, if you see. Okay? So kind of like the main feature of these three new polynomials is that they are zero at two of the three x values, right? But they're not zero at the third one. They are zero at two of the three x values. Is that making sense? In fact, you can kind of compute the value of the polynomials at the value that is not zero. So for example, what is what is L0 x of x0? That would be L0 x of what is x0? X0 was 1. Okay, that would be 1. So that would be 1 minus 3 times 1 minus 5. Okay, which is what, negative 2 times negative 4, and that gives you 8. Okay. The other two values for x, that like the polynomial, that particular polynomial is 0. Okay. How about the other two? So what would be, like, for example, L1x at x1? That would be L1x at what is x1? What is x1? X1 was 3. So that would be 3. And that would be 3 minus 1 times 3 minus 5. That's 2 times negative 2, which is negative 4. Okay. And again, it is 0 at all the other two values of x. Okay. I'm just kind of computing the value like at the non-zero answer. And then what is the last one? The last one would have been like L2x of x2. That is L2x. What is like the third value? What is x2? X2 was 5. So I'll put 5 here. That's 5 minus 1 times 5 minus 3. That's 4 times 2. That's 8. Okay. So what I'm saying is that of these three polynomials, right? So just to kind of recap what's happening, you know, you construct these three polynomials, right? They're zero at each of them is zero at two of the three x values, but it's not zero at the remaining value. Okay, and here I'm computing the non-zero value, like at the corresponding x value. Okay, is that okay, everyone, with me? Like what I have computed so far? You'll see why am I doing this like in two more lines. Like I'm almost ready. Okay, and now there's almost one more. There's just two more steps. Okay, I should have called this like step two, by the way. Sorry about that because I'm giving these steps, right? Like, and then step three is to rescale the polynomials by these values that you just found. So what do I mean by that? Let me copy again the polynomials. So these were like the three polynomials that we had found. And what I'm saying is that I'll rescale each of them. I'll divide each of them by this value that I just found, this non-zero value that I just found. So I'll do x minus 3 times x minus 5 divided by 8. Then I'll do x minus 1 times x minus 5 divided by -4. And then I'll do x minus 1 times x minus 3 divided by 8. Okay? Sure. And then what is the property of this new version of the polynomial? The interesting property that they have is that they are zero at two of the three x values and precisely one at the remaining x value, which is kind of like cool. So the next like the key property of these rescaled polynomials is that they're zero at two of the three x values, and they take the value one at the remaining x value. So they are zero at two of the three x values, and they are one at the other one, at the remaining x value. Yeah, actually, maybe it's good if I can show you a little bit about this in GeoGebra on how this is looking. Um, Sorry, let me see if I can bring this up for a second. That should give you some like insight. Okay, so let me see if I can share my screen for a second on GeoGebra. Okay, so what's going on here? Like maybe it's good to kind of like summarize what's happening for a moment. So the points that I was trying to interpolate were 1, 3, 3, 4, and 5, 6. Okay, so let me see if I can use different colors. This is the first one, this is the second one, and this is the third one. Okay, so those are the 3 points. So for each point, I'm kind of like constructing for each x value, I'm constructing a polynomial that is precisely 1 at that x value and 0 everywhere else. So for example, for the first one, the polynomial, um, was, let's call it f p1 of x was x minus 3 times x minus 5 divided by 8. Okay. Uh, oh, let's see. So let's see. Is this looking fine? Like this is. Yeah, like it looks fine. It's just like it's not super clear from the picture, you know. So let's see. What if I got? Yeah, this not. Oh, okay, okay. Like, yeah, yeah. Now, like, sorry. Like now I'm less confused. Like in the picture. So, okay. Now this makes more sense. Okay. So where, um, if you look at it, this polynomial, right? It is 0 precisely and at 3 and 5. If you look at this, where does it cross like the x-axis and 3 and at 5? Okay. Um, so it's kind of like useful. Like I should actually write down this, like, yes, like this will help everyone see what's going on. Okay, yes. And let's match the colors as well. Okay, now this is better. So, oops, I do want to show okay. Okay. So this polynomial is the one that's associated to the first point is 0 at the other 2x values, which is what you can see here. And at this x value, it takes the value 1. Okay, now it looks better. Okay, good, good, good. Now I like it. And then how about the other two? So the other two was x minus 1 times x minus 5 times -4. Let's put it like this. Okay. So this is with the red polynomial, so that's fine. Okay, so if you see at this red polynomial, right, the second one, now, now it is 0 precisely at the other two x values, which are 1 and 5. And at the red value, it takes value 1. Okay, so there it is. Like at this red value, it takes value 1. And the last one is x minus 1 times x minus 3 divided by 8. Okay, and this, let me do it green because otherwise it's a mess. Okay, and then the last one, the one that's with green, is 0 at 1 and 3, and at 5, it takes value 1. Okay, so kind of like what I want you to notice of these 3 polynomials is that they always become 0 at 2 of the 3 roots. At 2 of the 3 x values, and then they are exactly 1 at the remaining x value. Okay, so that is how these 3 ones look like. And then kind of like what you want to do is kind of like to rescale them. That would be like the next step. What I want to do is to rescale them to kind of like to make them pass through like the actual y values that I want. Okay, so for that, like what I'll do is just multiply by the appropriate y value. So for example, and that will be the last step. But for example, since like the for the blue point, for the blue point, the y value was 3. So what I will do is multiply this by 3. You see, so like now it passes through this point and it's still 0 at the other two ones. For the red point, since the value for y for the red point was 5, I multiplied the one in the middle by 5. And now, see, it's still 0 at the other two, but now it passes through the correct y value. And for the green point, since the value for the green point for y is 6, I multiply this one by 6. And now you see like the polynomials, kind of like each of them individually pass through one of the points and they are 0 at the other two ones. So basically what I'll do is kind of like just add them together and that will be the polynomial that I care about. So it's kind of like I kind of like broke down the problem into a problem about finding a polynomial. I may have said this earlier. But kind of what I did is like I changed the problem into finding. Basically, what I'm doing is trying to find a polynomial that passes through one of the points and is 0 at the other two points. And I'm doing that for every single one of them. You see? That's kind of like what the idea of the Lagrange polynomial interpolation is. So it's kind of like a polynomial, again, vanishes at two of the three, and at the third one. Oh, I had to divide by 8 because that was like that's kind of like to rescale it so that it has value 1. Like again, like if you let me ignore the 3 here. Um, I divided by 8 so that it would take value 1 here. Okay, because if it takes value 1, then it's just easier to multiply it then by 3 so that it takes value 3. You see, it's kind of like you first kind of like shrink it so that it has value 1, and then you re stretch it so that it takes like the correct y value that you wanted. So it's kind of like a game because if, for example, if I cannot rescale it by 8, right? Imagine if I don't rescale it by 8. So now the polynomial looks like this. If I don't rescale it by 8. And then you are like, okay, how do I get to this point? You basically would have to do these numerics in your head. Oh, first you shrink it to 1 and then you multiply it by 3. You know what I mean? So it's kind of like a way to do it in 2 steps to make it easier to kind of like work with it in practice. Uh, but yeah, this is kind of like this is like the easiest, better way to explain it. So you have these 3 points. Instead of trying to find directly the parabola that passes through them, you first find like a parabola that passes through one of them and is 0 at the other two, which is what you are seeing here. Okay. And it's useful that they're 0 at the remaining two values because then when you add them together, then you won't mess up anything. So kind of like what will happen, you'll see that in a moment. I'm about to write that down. That's the last thing I'll write. Kind of like the solution will be that the addition of the three polynomials. But for that to work, it was important that, to have this property that they are 0 at the remaining two values because 0 plus 0 doesn't mess up anything. You know what I mean? So kind of like the total polynomial is like a sum of the original three polynomials. Um, okay, let me write that. Like, this is like the last thing I wanted to write for today. So I'll write it down, and tomorrow I'll kind of like write it down in a more like algorithmic way, like a more precise way, so that you have it more like as a method. Um, well, it's just that this is like if you mean what we were working on like last week is a completely different thing, right? It's just like a different topic. uh like this course is kind of like a collection of topics. So this is like just like, okay, here's a different problem. Do you want to interpolate? This is how you do it. But yeah, it has nothing. uh well, I mean, right, but the roots, like this is kind of like for polynomial. I mean, uh right, but like the roots, like in the week from last week, it was kind of for any function, you know so you had a function, you're trying to find where it's 0. Here's a bit different because you have some points and then you're trying to find the function. You see? It's like a different idea. Like there, you had the function, then you're finding where it's 0. Here you have the points and you're trying to find the function. Like it's kind of like in reverse almost. Not quite, but it's kind of like more like in reverse of what we're trying to do right now. Um, so yeah, just to kind of like finish, like this is like the last thing I'll write. for today, and then tomorrow I'll kind of like write down the general formula so that you have enough time to do the quiz. So kind of like what I'm trying to say is that since we then want to pass through the points. Let me write this with a different color. So the points were again 1, 3, 3, 4, 5, 6. 1, 3, 3, 4, 5, 6. What you do is kind of like a combination of these polynomials. You take so the first one gets multiplied by 3, which is what I was saying. So you multiply the first one by 3. The second polynomial that we found, we multiply it by 4. And again, I'll write the formula, like the general formula more precisely tomorrow. And the last one, you multiply it by 6. Um, so that you have it here. So in other words, basically what you do is, so basically what I'm trying to say is that each of these rescale polynomials gets multiplied by the corresponding y value, and then they are all added together. So it works. You multiply each polynomial, each rescale polynomial by the corresponding y value, and then you add, and then add. But kind of like the cool thing about this method, again, it will become more clear tomorrow when I write it down. The cool thing about this method is that literally you didn't solve at all the matrix system, right? Like there was no matrix system that we solved, but it is equivalent to having solved the matrix system. That's kind of like the crazy thing. But it's just kind of like breaking it up into more like mini problems where each mini problem is like, oh, let's just try to find a single polynomial that passes through that point, but is zero everywhere else at the other points. And so once you break it up from that perspective, um, it kind of like facilitates like finding the correct answer, you see. Okay, so what I'll do is okay, I'm going to make available the quiz. You can take a 5 minute or 10 minute break if you want to do that before like starting the quiz because um, so I just made the quiz available. You can go take it unless you want to ask me something. I'll also stay like for a bit longer in the Zoom chat if someone wants to ask me anything else. Um, it depends on what pictures you mean. Oh, like you mean like on lockdown browser? I think on lockdown you're just supposed to you just show on your camera like the piece of paper where you wrote the solutions. That's all that you need to do. I mean, that's fine. Like, I still have to review them, but I was not expecting that's why we're doing the quizzes before the exam so that people have like a chance to work on that. So yeah. So like, don't worry about that. You can like, just like this time, try to kind of like make it more clear what you wrote. Um, basically the idea is like, so that like if someone wrote like 5 sentences and then they upload something which has like 40 sentences, like that's kind of like what you're trying to prevent, for like with this taking the picture kind of thing. But yeah, like it was like since it was the first time, I wasn't expecting like that to go perfectly, so don't worry about that. Yeah. Anyone else? Any other questions? I'll see you tomorrow then.